All right, so we will continue to work through lecture set 13, picking up with the example that we left off with on slide 22. We are, obviously we're not going to finish lecture set 13 this semester, but that's okay. We're going to finish all the material that we need for the course. Everything after that is just bonus material anyways. So this is, it actually kind of works out. I think it works out well that we're recording this lecture because some of the material we're going to talk about today won't be on the assignments, but it will be on the final. So it'll be nice to have the recordings to go over that material, especially when preparing for the final. All right, so with that being said, I'll just kind of get back into it. And last class, okay, so we left off on the second of 2 exercises, or maybe it's the second of 3 exercises because there's another test coming up in a bit. And we are talking about basically modeling the price of those antique grandfather clocks. And we have 2 different explanatory variables. So we have the number of bidders for the clock, and we have the age of the clock. So we consider 2 models. We have one model where, and the models are shown here, we have one model where we're only adding those 2 effects together. So we have y is a function of age and bidders. And then we have a second model where we have y as a function of age, bidders, and the interaction term between age and bidders. All right, and what we have done so far is essentially talked about how we can use the output from the fitted models to determine if the interaction term should be included. So we can use the t value and the associated p value. And we've basically just talked about how to use the models, which is something we've seen before. I mean, in terms of prediction, you can just plug in the values that you're interested in and get out a value of y the same way we did with simple linear regression, except that we have to plug in for each of the different points that the values enter into the model. So for example, what I mean is in part D and part E from last class, we had grandfather clocks that were 150 years old and had 15 bidders. We plugged those 2 values into the model and we ended up with a price of around $1,860.93. So what we're going to talk about today is more of the inferential parts and the model assessment parts. So the first thing we did last class is compute the adjusted R squared. This illustration that's shown on slide 22, this was to demonstrate how you would do it if you're only given R squared for the model. So this is how you would adjust the R squared given how you would adjust the R squared in any particular case to get the adjusted R squared. Now, we can also compute the R squared directly just by using the MSE and the MST, and we'll go through an example of that as well, which would be the easier way to do it. And given that we have a NOVA output, it would be more direct. Okay, so before I get back into that, I'll just start with I'll do that next. So we started with part B and then we'll go back to part A. It doesn't matter what order we do this in, so I'll just finish part B. Okay, so here we have the adjusted R squared for the model without interaction. Okay, so this is the model without interaction. All right, now let's compute the adjusted R squared for the model with interaction. Okay. All right, so let's do this in the traditional way just so that we have an example of both. Okay, so the adjusted R squared is 1 minus the MSE over the MST. All right, so our MSE for the model with interaction is given right here. And then the MST we need to calculate. So the MST is going to be, what would that be? 4,791,195 divided by 31. Okay. I don't have that exact number available. Right. So then the adjusted R squared for this model is going to be 7,809 divided by 4,791,195 over 31. And that's going to give us 0.951. Okay. So that would be the more true, that would be computation of the adjusted R squared based purely off of the values from the ANOVA table, which is the easier way to do it, rather than having to adjust the R squared. Okay. All right, so we'll do part C next, because it's directly follows this question. Okay, so part C says, do the adjusted R squared values give evidence that the interaction term should be included in the model? All right, so essentially what we are looking for here is which value gives the higher adjusted R squared. So in this situation, we can see that the difference in the adjusted R squared values is about 0.7 units, so about 7% difference. So that would give us evidence that we should include the interaction term because we are explaining more information in the response variable with the interaction term than we are without the interaction term. Or more simply, because the adjusted R squared is higher for the model with the interaction term, that would imply that that model is a better fit to the data. Okay. So since the adjusted R squared value is higher for the model with interaction, the RA squared implies the model with interaction is a better fit for the data. And so therefore, we should, or therefore there is some evidence that the interaction term should be included. All right, any questions? So if there's no questions, we can go back to part A. So part A says, do the model utility tests give any evidence that the interaction term should not be included in the model? Okay, so basically, when we look at the output, we have this F value here, okay? So there's actually two different model utility tests that are being conducted because we have two different ANOVA tables. So we have the F value that I highlighted, which is for the interaction model. Okay. And then I have the F value here, which is for the additive model. Okay. So I called it the additive model because there's just two terms being added together. The interaction model, you have multiplication, so that's why it's not additive. This could also just be model without interaction. That would be the same thing. Okay, so to answer this question, essentially all we have to do, well, we can look at it in two different ways, but the easiest way to do this is to say, okay, I have my F value for the model with interaction. This F value is 195.1829. So if I consider the test that is being associated with this value, okay, I would have the following. Okay, so I have step 1, H0, beta 1 equals beta 2 equals beta 3 equals 0. Okay. Versus HA at least 1 beta j does not equal 0. J equals 1, 2, 3. Okay. So I have that sort of standard ANOVA type test. Everything is equal against one thing is not equal to 0. Okay, and again, this is the same thing as H0, the model is not useful, versus HA, the model is useful. It's the same style of test. Or that is the same question. Okay, so then on step 2, I would have my significance level. On step 3, I have my F value, which is 195.1829. Okay, so then on step 4, I can take the critical value or the p-value approach, right? So if I take the critical value approach, okay, I'm going to go to my F table. I'm on 3 and 28 degrees of freedom, right? So 3, 28. All right, so I just need to pull up my F table here. So here's 3, here's 28, 0.05, 2.95. So that's my critical value. And if I was to take the p-value approach, it's pretty obvious, or hopefully it's obvious, that our test statistic is much larger than the largest listed critical value, which means that the p-value is going to be less than 0.005. Okay. So then on step 5, I would say reject H0. And then on step 6, I would say at the 5% significance level, the data provide sufficient evidence to suggest that the model with interaction is useful. Right, so we rejected the null that all the coefficients are equal, or that all of the coefficients are equal to 0. So that would imply that at least one coefficient is different from 0, which means that the model is useful in terms of explaining the relationship between price and those other variables. Okay, and then it says, does it give any evidence that the term should not be included? Okay, so in terms of the question, okay, the model utility test does not give any evidence that the interaction term should not be included. Okay. Any questions? Okay. All right, so part D asks, how else can we test whether or not the interaction term should be included in the model? Okay, so what we have done so far is basically model comparison via the adjusted R-squareds. So based off of the adjusted R-squared, we said the term should be included because it yields a higher value. Then we looked at the direct model utility test. The model utility test is telling us that there is evidence that the model is useful. So the model with interaction is useful, which implies that that term might be useful. But what if we want to test the term directly? So we want to just test the interaction term. Okay, well, what we can do is we can consider a formal statistical hypothesis test designed to assess additional terms in statistical models. Okay, so for example, a test that compares y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 x2 to y equals beta 0 beta 1 x1 plus beta 2 x2. Okay, so we've been considering two different models. This model with interaction terms, so beta 1 or beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 x2 against the reduced model, which is beta 0 plus beta 1 x1 plus beta 1 or beta 2 x2. So if we can consider, or if there's a test that allows us to compare those models to each other directly, that's the same thing as comparing the effect of the interaction term. All right, so what is this test called? This test is called an extra sum of squares F test. So the idea is this test takes two models, what we call a reduced model and what we call a full model or a bigger model. And it will, as long as the reduced model is a subset of the full model, this test is used to assess the effect of the extra terms. So in our situation, this works out really well because we are able to assess the effect of that interaction term against those main effect terms. Okay. So just like any other test, this can be carried out in 6 steps. So the hypotheses are that the reduced model is adequate against the full model being required, significance level. On step 3, we have our F statistic, which you can see is a ratio of the difference in the sum of square errors for each model divided by the sum of square error for the larger model. And then we have our F value, or our critical value or p-value approach, which is conducted in the usual way. And then we can determine if we should reject or not reject, and then we can interpret the result of the test. Okay, so for our model, we would have the following. Okay. Oh, and the assumptions of this test are the same as the assumptions we've been using for the regression line in general. So assuming that all the assumptions are checked for the regression line, you can run this test. Okay, so we have a reduced model, which is of the form beta 0 plus beta 1 x1 plus beta 2 x2. Okay. The sum of square error for this model is given on slide 22. So the sum of square error is 514,035, and the DF error is equal to 29. The full model is going to be, in this particular situation, the model with interaction. The sum of square error for this model was 218,646, and the DF error was equal to, or is equal to 28. Okay, so on step 1, we have H naught, reduced model is adequate, versus HA, the full model is required. On step 2, we state our significance level. So we can just use the standard 0.05. On step 3, we compute our test statistic. Okay, so the test statistic is SSE reduced minus SSE full divided by the DFE reduced minus the DFE full. And that's divided by SSE full divided by DFE full. All right, so this is going to be 514035 minus 218646, okay, divided by 29 minus 28 divided by 218646 over 29. Or sorry, 514. Okay, and this gives us 20.746. 20.726. All right, so it's an F test. So on step 4, we can take a critical value or p-value approach. All right, so if we take the critical value, all right, our F value is going to be on the degree of freedom error reduced minus the degree of freedom error full, degree of freedom error full, and alpha. So this is going to be an F value on 1, 29, and 0.05. Or here, I'll actually just, for completeness sake. Right, so this is going to be 29 minus 28, 29, 0.05. Yeah, in the denominator, SSE full divided by DFE for the full. Yeah. Oh, I see. Because I put the reduced ones there. Right, yeah. Okay, yeah, I had it right the first time then. Just check the value really quick. Yeah, that's the full. Okay. And then this is 28. Okay. There we go. There we go. Equals. Okay. Good catch. Thank you. All right. And then fortunately, it doesn't change the conclusion. Okay, yeah, there we go. Good, good, good. Okay, and then that doesn't change the critical value. Okay. So we go down here now. 129. No, 128. Yeah, 128. SSE full. $128, 0.05, 4.20. Okay. Make sure all that stuff. Cool. So that gives us our critical value, and then the p-value. Okay, so if we take the p-value approach, our test statistic was 37.829. Okay, so 37.829 is going to be bigger than 9.28, which means the p-value is less than 0.005. So we can reject H0. All right, so then on step 6, we can say at the 5% significance level, the data provide sufficient evidence to suggest the full model is required. Okay. But again, the point is, because the full model is only the one additional term, which is that interaction term, the result is that the interaction term is required because the only difference between the two models is that term, right? So that is the interaction term is required. Okay, any other questions or corrections? Thanks for catching that again. All right. Okay, so that's good. It's a good progress. So we still have some time left today. So we're going to talk a bit about the next topic within the material. Okay, so which is, I guess we can call this like a bonus topic because it doesn't appear on the assignments, but this is still something that if we can get through sufficiently, I'll use on the final. So the unit itself is not very complicated. It's basically just, we know what an MLR model is. We know about the tests and the diagnostics that are associated with the MLR model. I talked before about how MLR model or ANOVA models are actually special cases of regression models, but they use categorical variables rather than continuous variables. So what this unit is about is how we actually include categorical variables in our model. So to understand this, we're going to use a data set that measures the number of flowers that grow on meadow foam plants as a function of two explanatory variables: light intensity, which is continuous, and light timing, which is categorical. Okay. So again, we have two factors, intensity and timing. Light intensity we will treat as continuous because it's numeric. Light timing we have to treat as categorical because it's a label. So you can see that the light timing variable has two levels, early and late. All right, so what this means is that we're actually evaluating the growth of the plants, or the flowers rather. We're actually counting the number of flowers on each plant at combinations of the intensity and timing schedules. So there's 12 different treatments in total. So 6 intensities for early light, 6 intensities for late night or late light. So 6 plus 6 is 12. Okay. In each chamber, for each treatment, there's 10 total plants. So we are going to take the average number of flowers across all of the plants as our response variable. And then we're going to fit a regression model to see if we can predict the number of flowers that grow based off of these two variables. All right. Okay, so here's a visual look at the averages, just for more clarity on the design, right? So you can see here, for example, we have light intensity, we have the late and the early lights, we have the and then we have the average number of plants that have grown across the two replications. All right. Okay, so here's the data from the previous slide superimposed onto a scatter plot. So we have number of flowers that grew on the y-axis, we have the light intensity given on the x-axis, and then we have a color code based off of whether it was early or late night. So you can see that in this situation, for each replication of the experiment, we're counting that as separate values on the plot. So that's why we have stacks of 2 green and 2 red dots at each of the different intensities. Okay, so this plot is simply the data shown here, okay, just directly being superimposed. Okay, and our objective is just to fit a model to represent flower growth as a function of intensity and the timing schedule. But what makes this different is that, again, the timing schedule is categorical, so it can't be included in the same way as the intensity value. All right, any questions? Okay, so here's the simple model, or the simplest model that we can consider for this experiment. So we propose y, which is the number of flowers, is equal to beta 0, some intercept, plus beta 1 x1, where x1 represents the timing, so it's a continuous value, plus x2, where x2 represents, or sorry, x1 is the intensity, so it's a continuous value, and x2 is the timing, early or late. Okay, so how do we actually include x2 in the model? What we do is we introduce what is called a dummy variable. So a dummy variable, or an indicator variable, is a very simple style of variable. It takes on 2 values, 0 or 1. Okay, so this value, or x2, is now going to either be a 0 or a 1, depending on the timing schedule. So all we actually have to do here is assign one of the levels as the 0 level and the other level as the 1 level. Okay, so that's essentially what this boils down to. So for our model, we're going to say that if x2 is equal to 1, the value is in the early light group. And if x2 is equal to 0, the value is in the late light group. So we were, in this situation, we are referring to late light as the reference level and early light as the active level. Right. So the effect that this has on the model is actually very straightforward. Basically, if you are in the reference group, so the late light group, beta 2 gets multiplied by a 0, and we just have an SLR model. If you're in the early light group, beta 2 gets multiplied by a 1, but we still just have an SLR model because the intercept becomes beta 0 plus beta 2 plus beta 1 times x1. So what we have created here is a system of 2 parallel lines. So essentially, when a dummy or a categorical variable is introduced into a model and there's no interaction terms, all that value does is shift the intercept up or down. Okay, so you can see here that theoretically, we're just saying if in the active group, so the early light group in the illustration, shift the intercept by the coefficient that's associated with that value. Okay, so here's the data laid out in terms of the x1 and x2 values that we're actually going to use to fit the model. So we have all of our response variables, which are the y values. We have all of our x1 variables, which are the light intensity. And then x2s are just zeros and ones, corresponding to whether they're late or early. So if we were to think about what the data looks like, it would be columns 1, 2, and 4. So the Y, X1, and X2, and we wouldn't even have the timing labels being used in the actual process. Okay, any questions? All right, so here are the two models that are being superimposed, or the fitted models superimposed onto the graph, just to further illustrate this idea of parallel lines. Okay, so the late group is the early group. So this model here is Y is equal to beta 0 plus beta 1 X1. And then the early light is the active group. So this line here is beta 0 plus beta 2 plus beta 1 X1. Okay. So you can see that the slope of the two lines is exactly the same. So these lines are parallel to each other. They have the effect of light intensity on the response variable is identical for each group. The only difference is where they start. Okay, so where the y-intercept is. So here is the fitted model. So we have yi hat is 71.3058 minus 0.0405 x1 plus 12.1583 x2. Okay, so the model is showing us that as light intensity increases, the number of flowers decreases. But it's a very small decrease. But the more intense the light, it tends to drive the number of flowers that blossom down. Okay, so we have a couple of questions. What is the y-intercept for the late group? Okay, so first off, recall x2I is equal to 1 if early and 0 if late. So here we're going to have yi hat is equal to 71.3058 minus 0.0450 x1I plus 12.1583 times 0. Okay, so that means that we have 71.3058 minus 0.0405 x1I. Therefore, B0 equals 71.308 for late group. All right. Okay, so what about for the early group? Well, in this case, we're just going to shift the intercept by the coefficient for x2. So we're going to have yi hat is 71.3058 minus 0.0405 x1I plus 12.1583 times 1, which is equal to 1, carry the 1, 4, carry the 1, 6, 4, 3, 83.4641 minus 0.0405 x1I. So therefore, B0 equals 83.4641 for early group. Any questions? Okay. So in terms of interpretation, understanding what the coefficients are doing is actually very straightforward, and it follows directly from our initial discussion on MLR models. So you might recall that at the start of the lecture set, we looked at MLR models where we only added values together. And then we talked about how the interpretation is pretty much exactly the same for those models as it is for SLR models, except that we're conditioning on the other variables. That's the same thing here. The only difference is for X2, instead of talking about a 1 unit increase, we're talking about a shift from the reference level to the active level. Okay, so for example, this first interpretation here, okay, this is for beta 2. Okay. So what beta 2 is, or what B2 is telling us, is as we shift from the late group to the early group, we are going to expect an additional 12.1583 flowers to grow. Okay, so that coefficient is telling us that as we move from the reference to the active group, you expect to gain the coefficient, which is 12.1583. Okay, so we can write, we expect meadowfoam plants that receive early light to produce 12.1583 more flowers than meadowfoam plants that receive late light. And that's true no matter what the light intensity is, because all that term is doing is shifting the intercept. So no matter what light intensity value you observe, you're always going to expect 12.1583 more flowers from the early light group. Okay, the second interpretation is for beta 1. This is just the standard interpretation of a slope value. And it doesn't matter what group you're in because there's no interaction. So for beta 1, we can write, as the light intensity increases by a unit, we expect the number of flowers that appear on the plants to decrease by negative 0.0405. So every additional unit of light intensity causes the number of flowers to reduce by 0.04. And we don't need the negative here. Decrease by. Okay. Now the last 2 points are simply just interpretations of the intercept values. Okay. So this is beta 0 when x2 equals 0, and this is beta 0 when x2 equals 1. Okay, so when you are in the reference group, which is the late light group, you're going to expect 71.3058 flowers to grow when there's no light intensity. This is the intercept. And when you're in the early group, you would expect 83.4641 flowers to grow when there's no light intensity. So these are just the 2 intercepts. So basically what a categorical variable does is it includes a shift between levels into a model, and it just creates a series of, when there's no interaction term, it creates a series of parallel lines. So you have multiple intercepts that you have to consider, but otherwise the the interpretation of the values is essentially exactly what it was for the additive MLR model we began looking at the start of the lecture set. Right. Any questions? All right, so in general, if we want to include a categorical variable into a regression model, it doesn't actually matter how many different categories appear in the variable. So we looked at a very simple situation where we only had 2 levels, but you could have categorical variables that have 3, 4, 5, 6, 7, etc. different levels. Okay, there's no restriction on how many levels the value has or the variable has. In order to include it in the model, the most common situation is to use a series of dummy variables. So for every k levels in the categorical variable, you would use k minus 1 dummy variables. So for example, we had a situation where we had k equals 2 categorical k equals 2 categories in the variable. So we used k minus 1, which is 2 minus 1, which is 1 dummy variable. If we had a situation where there were 3 categorical variables, then we would use 3 minus 1, which is 2 dummy variables. If we had 4 categories in the variable, we would use 4 minus 1, which is 3 dummy variables. The only other condition is that for every dummy variable, you have to have the exact same reference level. Okay, so whatever the reference level is for the first dummy variable, that has to be consistent for every other dummy variable in the system. Okay. Any questions? Okay, so we looked at an illustration where we considered the introduction of a categorical variable or a dummy variable and no interaction term. What happens if you interact a dummy variable and a continuous variable? Well, the result is that you would now have a system where the lines are no longer parallel. So when you mix a continuous and a categorical variable, you're going to shift the intercepts and you're also going to change the slopes of the line. So you're creating systems of non-parallel lines. Now for the metaphone plant experiment, if you consider each group separately, we have the 2 simple linear regression models shown below. So we have an SLR model for early group and we have an SLR model for late group. So that's as if we split the data into 2 different data sets and fitted to each one separately. Okay, so we can see that we have these 2 slope values associated with the groups that are very, very similar. They're almost equivalent in value. This would imply that realistically, we probably don't need to consider an interaction term because the values are so close, but we will anyways just for illustrative purposes. But just to give a little bit of insight into when you might want to consider an interaction, it's when, if you were to consider the groups separately, you see very different values for the slopes. So here is the MLR model if we consider interaction. Now, this system is more difficult to interpret because of the effect of the interaction term and because of what it does to the response variables. So in general, we can kind of highlight what the terms mean. For example, given the same declaration, so since x2 is 1 for early and 0 for late, that means that B0 or beta 0, this value here, this represents the intercept for the late group. So this is the intercept for the reference level. And therefore, this value on its own is going to be the slope for the late group, which is the slope for the reference level. Okay. This value here, B2, this is the expected change in the number of flowers that grow between the late and the early groups, but it only applies to the intercept. And then this term here, which would be B3, okay, this term actually represents the difference in the slopes. So when you shift from the reference to the active level, this quantity gets added to the slope, and that gives you the change in the slope for the other group. So because the interaction term is present, we no longer expect exactly parallel lines. So B2 is only relevant when x1 is equal to 0. And B3 represents the change in slope that must be taken into consideration for every unit increase in the light intensity. Okay. So you can see on slide 40, I've plotted the two different lines against one another. So the green dashed line and the red solid line. You can see that the green dashed line is actually very close to being parallel, and that's just because the interaction coefficient is so small and there really isn't a significant interaction between the two groups. But again, just for illustrative purposes, we're going through this particular exercise. Okay. So we already expected that this would be the case based off of what we discussed before. But essentially, by going through this exercise and looking at the fit of the line, we're just confirming that we don't really need an interaction term here. We can still test this using a t-test or an extra sum of square f test. But given how close to parallel those two different lines were, we wouldn't expect the interaction term to be significant for this particular illustration. Okay, so to test if this, if the interaction term is useful, we can use an extra sum of square f test, or we can use just a t-test about the B3 value. Okay. So, okay. So basically what we have here is a reduced model y equals beta 0 plus beta 1 x1 plus beta 2 x2. And then we have a full model y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 x2. Okay. Okay. So okay, recall, or so if we were to test this, we would have step 1, H naught, the reduced model is adequate versus HA, the full model is required. Okay, and then on step 2, we would have alpha equals 0.05. So we actually just worked through an illustration of conducting an extra sum of square F test. So we know that the formula for the F value for the extra sum of square F test. So there's actually a trick where you can get the F score directly from the T value. And that's the purpose of this illustration. So this is an example of the same type of test, but just finding the test statistic in a different way. Okay, so if the F value, so the test statistic, follows a F distribution where the first degree of freedom is equal to 1, then F equals T squared. Okay, so this is just a little bit of a theoretical relationship between an F value and a T value. And basically the relationship just says if the first degree of freedom is a 1, you can actually square the T value to get an F value. Okay, so in this illustration, recall T is equal to B3 minus beta 3 over the standard error of B3. So this is going to be B3 minus 0 divided by the standard error of B3, given that we're just testing whether or not beta 3 is different from 0. Okay, so B3 is given to us on slide 38. That's the 0.001210 minus 0. And then we're going to divide by the standard error, which is 0.010515. Oh crap, I skipped something. Okay, I'll go back, sorry. I don't know how I missed that. Okay, so this is so therefore F is equal to this value squared. Okay, so then if we take the critical value for the p-value approach, we're going to have 1, and then we're going to have the difference. So this is the difference between them, and then we're going to have DFE for the full. So the DFE for the full is going to be the number of observations minus the number of model parameters minus 1. Okay, so in this illustration, we had 1, 2, 12, we had 24 values. So 24 points on the graph if you want, or 24 observations, minus the number of model parameters minus 1, 0.05. So this is F on 1 and 20, 0.05. All right. Oh, this one. Okay. And then the p-value. So given that our test statistic is 0.013, we can show that the F value is less than 0, or is less than the smallest value. So therefore the p-value must be greater than 0.01 or greater than 0.1. Okay, so we do not reject H0. And then on step 6, we can just say at the 5% sig level, we do not have sufficient evidence to suggest that the full model is required. Okay, so that's just another, this is the exact same test that we just talked about. So the extra sum of square F test. It's just showing how we can get to the test statistic through a slightly different formula, because the first degree of freedom is equal to 1. So this is something we can do whenever the difference between the two models that we're comparing is only one term. Okay, so just before I wrap up here, I need to go back and just talk a bit about the parameters in the model. Okay, so B0 is 71.623. Okay, so this is expected number of flowers when light intensity is 0 and light is late. Okay, so that is x1 equals 0, x2 equals 0. Okay, B1 is negative 0.041076. So this is expected change in number of flowers in late light group when light intensity increases by 1 unit. Right? So this is still x2 equals 0, but x1 going up by 1. All right, beta 2, 11.52, 11.523. Okay, so this is so this is the expected number of flowers when light intensity is 0 and light is early. Okay, and then beta 3 represents the difference in slopes between the two lines. So we can say this value is 0.00121. Okay, so for every unit increase in light intensity, we expect the number of flowers in the late or in the early light group to be 0.001210 units higher than that of the late light group. Okay, sorry, that was a bit rushed at the end there just to fill it in, but those would be the general interpretations of the values. Okay, and then again, what the interaction does is it just changes the role the slope plays, or it changes the value of the slope when you shift between the levels. So interaction models should create systems of not parallel lines if it's significant, and the inclusion of a dummy variable without interaction creates a system of parallel lines. So they only differ in the intercept term, the B2 term. Okay, so I'll stop there. And on Tuesday, we'll do some review for the final, and then I'll go through an example of a more complicated example of this material so that you have an exercise to use. And yeah, assignment 6 is due tomorrow. I have office hours today at 10 online and in person. And otherwise have a good weekend, and I'll talk to you guys on Tuesday.